This is example 2 in Module 7. So we have a setup where an electron is pulled off of the negative plate of a capacitor. It's accelerated through the interior of the capacitor because we know that there's an electric field inside the capacitor. And then it escapes the capacitor through a small opening, say a pinhole. And then it is, essentially it travels into a uniform magnetic field, so that we know when a charged particle goes into a uniform magnetic field, it's going to undergo circular motion. And it travels around a half circle. And what we want to do is determine ultimately what the diameter of that half circle is. We know that the capacitor is connected to an EMF that has some given voltage, so we know what the potential difference between the capacitor plates is, and we know what the magnitude of the uniform magnetic field is. Since it's an electron, we know what the mass is, and we also know what the charge is. So we know that this is, let's start off with the uniform circular motion portion. So if we forget the fact that the electron comes off of a capacitor and just consider an electron that's traveling through a uniform magnetic field, we know that it's going to undergo circular motion. And the requirement for circular motion is that the radial acceleration, the magnitude of the radial acceleration, I should say, has to be equal to the magnitude of the velocity squared over the radius of the circle. So for a particle traveling around a circle, it has to have a radial acceleration whose magnitude is equal to v squared over r. That means that the radial force, so I'll just write F subscript r, has to be the mass times the radial acceleration, which is the mass times v squared over r. And the radial force here is provided by the magnetic force. So we know that this is equal to the magnetic force. And we know what the magnitude of the magnetic force is. It is QVB sine of theta. Now the angle theta is the angle between the velocity vector and the magnetic field. This is going to be 90 degrees, so sine of 90 degrees will be 1. Here I'm going to explicitly write an absolute value sign around the charge, because we're talking about magnitudes of forces, and magnitudes of forces are always positive. So the charge in this equation could be positive or negative, but for negative charges, the magnitude of the field is still going to be a positive, or excuse me, the magnitude of the force is still going to be a positive number. So I'm going to write an absolute value there. All right, so let's look at what we have here. Let's take this equation and simplify it a little bit. Mass, I have a velocity on both sides, so I will cancel that. I'm going to move r to the right-hand side. So I have this equation here. Let's look at the terms in this equation. M is the mass of the particle, which is the electron. And again, hold on, I'm going to put the Q to the outside. There we go. So mass of the electron, if we are looking at the equation sheets that are used on the exams, this is going to be M subscript E. So that tells me that I know that this is not just some arbitrary unknown mass. It's the mass of an electron, which is a constant that can be looked up in a table. V is the velocity of the electron, which is unknown. We don't know what this is. Q is the absolute value of the charge of the electron. So that's going to be the absolute value of the negative elementary charge, which will then just be the elementary charge. B is magnetic field strength. Which is given to us. And R is the radius of the circle, which is going to be the diameter in the figure divided by 2, which is also unknown. In fact, the problem is asking us to determine what that diameter is. All right, so we have one equation and two unknowns. That means that we need at least one more equation to get rid of one of those unknowns. So let me scroll down here a little bit. we've only looked at the circular motion part. There's also motion that's occurring inside the capacitor, and so let's look at that for now. Let's look at the motion inside the capacitor. So if I draw the capacitor here, I have the negative plate and the positive plate. The electron comes off of the negative plate. There is a uniform magnetic field inside of this capacitor because we're told that it's an ideal parallel plate capacitor, and we know that those types of capacitors have uniform fields inside, and the uniform field points from the positive side to the negative side. And we also know that an electron is going to be accelerated in the opposite direction of the field, so this makes sense. The electron is going to be accelerated to the right while the field points to the left. Now, ultimately, what we'd like to do is figure out what the velocity of this electron is. So if we want to know what the velocity of the electron is as it passes through a uniform electric field, there's a couple of ways we could do it. We could try to apply Newton's second law, which would give us an acceleration, and then we would have to use the kinematics equations. But if we consider Module 3, there's actually a simpler way to do this, because Module 3 was concerned with electric potential differences and how that's related to the potential energy change experienced by charges that move through that. And we know that if we have a change in potential energy, we'll have a change in kinetic energy. So we're going to apply conservation of energy here. And so if I do a standard conservation of energy setup, I usually say, okay, I have some initial state or position. That would be the electron right before it leaves the plate on the left. And right before it leaves the plate on the left, it doesn't have a kinetic energy. All right, so it starts from rest. It's accelerated off the plate. And its potential energy, we're actually free to choose wherever we want zero potential energy to be. So let's choose zero potential energy to be on the left plate. It's only changes in potential energy that ever show up in physical problems. So setting zero, we could have chose the left or right plate to set the 0 point for the potential energy. We would get the same change in potential energy. So now we need to consider the final state, and the final state is going to be the position of the electron after it experiences the acceleration of the electric field. So the electric field outside the capacitor is 0 because this is an ideal parallel plate capacitor. So what we want to do is consider the final position to be right as the electron is leaving the uniform electric field. Now, as it leaves, it's going to have some kinetic energy, and its kinetic energy, whatever it is, will be 1/2 mv squared. It's also going to have some potential energy. This potential energy might be negative, but we do know that the potential energy for a particle or charged particle that travels through some change in electric potential is going to be Q delta V. All right, so the change in potential energy is equal to the change in electric potential times the charge. So now we can write down our conservation of energy equation, which is 0 plus 0 is equal to 1/2 mv squared plus Q delta V. Now Q is the charge of the electron, and this has a negative sign in it. So the electron loses potential energy as it travels to the right, which is required for it to gain kinetic energy. And then delta V is the electric potential difference between the left and right plates. And so that is going to be the potential difference of the EMF that is connected to the capacitor. The velocity is, again, the velocity of the electron after it leaves the capacitor, and the mass is the mass of the electron. All right, so let's look at what we have so far. We have this equation here, which relates the velocity to the radius. We know that the radius is equal to the diameter that we are after divided by 2. And then we have this equation, that relates the velocity to the potential difference of the plates. So let me just summarize everything that we have. And I'm going to write this now in terms of the parameters that we're either given or we know as constants. Okay, so I had mv is equal to the elementary charge times the magnetic field strength times diameter over 2. And I have 1/2 mv squared is equal to negative QE, which is going to be negative. Electron is negatively charged, so that will be little e, big E. And let me put a subscript here for the masses to indicate that these are constants that we know. So I'm after the diameter d. So let me just take the second equation, solve for velocity, plug it into the top equation, and then solve that for d. So I've got mass of the electron, v squared, is equal to 2 times this. All right, so just do some algebra, solve for v. Now take this and plug it in to the top equation and solve for d. So this equation now is what we want to solve to get this this diameter d. Alright, now that's pretty much it. I could do a little bit of simplification if I wanted. So I've got a mass in the numerator and denominator, charge, magnetic field, stuff like that. So I could simplify this a little bit, but this would be correct. Let me just go ahead and simplify it just so that we can see what that looks like. So I can move this stuff here into the square root, but I have to square it. So if I do that in all of the steps, this would be a 4 me squared over e squared b squared. Now I can put that underneath the square root. And if I have two square roots multiplied by each other, I can put them together underneath one square root. And now I can start canceling stuff that's in the numerator and the denominator. So I've got a 4 and a 2 in the numerator, so I'm going to have an 8 up there. I've got a mass squared in the numerator and 1 in the denominator, so that'll be the mass. And then I've got, let's see, I've got a charge squared in the denominator, so I'll have 1 little e there. And then I've got magnetic field strength squared in the denominator, and I've got the potential difference between the plates of the capacitor in the numerator. And there you have it. That's the diameter of the circular motion that's shown in the figure.